cover. Let's start off with this. Let me open up my slideshow. And you've seen these variables before. Let's go ahead and just focus on the main ones right here. The main one that I want you to write in. Go ahead and write in this. So you see in front of you all the blanks. You've seen them on every single set of notes. Let's go ahead and just do the new ones so we can focus on getting as much practice as possible today. Let's keep the phones away if you're getting distracted by them. Let's go ahead. I want you to write down temperature, degrees Celsius, a little subscript degrees Celsius. It's happened again, at least it's not the computer this time. Temperature, degrees Celsius. And then you're going to have this equation. You might as well write it over here. I'm not sure if I lost you guys at home or not, but the lights went off here. V sound equals 331 plus 0.6 times temperature in degrees Celsius. And I'm just going to put an extra parentheses around here. So you're going to, whatever, if I knew that today was 25 degrees Celsius, if I knew Fahrenheit, I'd have to convert to Celsius. But if I knew it was 25 degrees Celsius, all I'd have to do is take that number, multiply it by 0.6. So don't write this part in, but this is all I would do. If I knew this degrees Celsius, I'd just take that, multiply it by 0.6, get that answer and add 331 to it, and I'd know how fast sound was traveling. And then on your equation sheet that you'll see on the test, the counting equation sheet does it looks like there's more than one thing here. That's why you want to be familiar with this equation. All you're doing is taking the degrees Celsius, plugging it in for that. And I'm not going to make you do a conversion from Fahrenheit to Celsius. I'll give you the temperature Celsius on any of these problems. You got it? Okay, so some of today's a review, some of it's not. First thing, highlight this. Sound wave is a longitudinal mechanical wave. You're almost guaranteed to be asked that. And so let's just look at why it's a longitudinal mechanical wave. Go ahead and underline it. Keep cell phones away unless you're doing the right thing. And so it's longitudinal because you have compressions and rarefactions. Everybody see that? Like until now, we usually drew this and said these are the compressions and these are the rarefactions. And here's another compression. Here's another rarefraction. Well, in reality, these are three-dimensional all around. And actually, if I can, this is only two-dimensional. If it's two-dimensional still, if I could have it go towards you and away from you, it would be three-dimensional. If anybody around you is talking and you're close enough, you can hear them, whether you're above them, below them, on the side of them. So just want you to first of all put that together, that when we were in a previous lesson, we looked at this, compressions and refractions. That is the same thing here. It's just this right here. If I was going to draw, but now in reality, it's all over the place. So it's longitudinal because the vibrations are back and forth, while the wave's traveling outwards. It's mechanical because these are all particles. So you'd see all these particles in this little area. So this is a picture representation of what's really happening. See how these particles, how they're just bouncing off of each other as you have the wave energy going outwards. These are going back and forth. And notice how this particle is going to return here. See how it comes right back to the same spot? You can follow the energy going out, but the actual particle itself returns because it's mechanical. And then we're going to have some problems in this unit where we talk about echoes. And so when you're thinking about an echo, when you're thinking about an echo, if I was far enough away from that wall, and the true meaning of an echo is if you can sense your voice again, if there's a 0.1 second interval between when you say something and when you hear it back, it's considered an echo. And if it's too quick, call it reverberation, because it's just your voice just sounds weird. It doesn't sound like it's the same thing over again. But an echo, take a look. If I have an echo off this wall, the echo has to hit the wall and come back. Everybody see that? Has to hit the wall and come back. And so sometimes I'm going to give you the time or the distance of the echo. Sometimes I give you the time or distance of the wall. So see, this is the distance to the object that the echo is reflecting off of, but this is the actual distance the echo returns. So we're going to draw some quick pictures as we do these problems, and we have to kind of think through the problem in order to make sure we have all our information correct. So let's go ahead. I want you to do a little drawing with me. You're gonna do a little drawing with me. Stop one way and listen. So here we have a person. Go and draw a little person. And we are going to hear the echo off a mountain. So let's go and draw a little mountain over here. And the person's going to hear an echo off the mountain. Well, the mountain itself is 500 meters away. Is that how long the echo is going to travel? 500 meters? What does the echo have to do? It has to go there and come back. So let's go ahead and draw this. So this was the actual distance. See how they gave you distance to the mountain? Well, I'm going to follow the echo. The echo has to, I don't know why that spiked. Echo has to go there and come back. So what's the actual distance of the echo? Yeah. Everybody see that? Everybody with me on there? So the distance we're going to use, the x we're going to use is 1,000 meters because we are following the echo. The echo traveled twice this distance because it went all the way there to the mountain, but it also came all the way back. And then they told you, okay, how long would it travel? T equals question mark. Make this givens list over here. And here we're telling you the velocity. In this unit, I'm going to start telling you just the temperature and you're going to calculate the velocity. But in this case, the velocity is 340 meters per second. So go ahead and do the math. B equals x over t. And t, when I rearrange that, t equals x over v. So t equals at 1,000 meters to go there and back over the time, which or v, the velocity of 340. So get that answer, and that's going to be the answer to this question. So the key here is they gave you the time to the meters to the mountain, but they didn't give you the meters to actual echo travel. Here we're asked about the echo. So since we're asked about the echo, we have to realize that distance that the echo traveled is actually twice as long. It had to get to the mountain and it also had to get back. Did you get your answer? Just type it in and you should see 2.94 seconds. Is that what you got? Okay, good job. Let's draw another picture. Okay, so we have a person. We have a wall over here. And bless you. An echo off the wall takes 5 seconds to be heard. So 5 seconds to be heard. Is that just to the wall or is that to come back? Yep, and come back. So this time is 5 seconds. That's to go there and come back. And the velocity is 343 meters per second. And notice what they do here. What is the distance to the wall? So what is this? So therefore, we don't want the time to the wall and back. What do we want the time of? Just to the wall, right? So what are we going to have to do to that 5 seconds to make it just to the wall? Yeah. Yeah. So you're going to end up having to just to the wall, the time's not going to be 5, the time's going to be half of that, so divided by 2. So now we have x equals v times t. That comes off of this equation too. V equals x times t. So x equals v times t. You get that equation. So go ahead, use that time, use that velocity, and get your answer. How far does that echo have to travel? Not echo, actually. How far is that wall? We're not concerned with echo anymore. We already cut that time in half because we just want to find the time it takes to get to that wall. And you should have got 857.5. So when we plug in our numbers, the 343 and the 2.5, we end up getting 857.5 meters. And that's going to be the distance there. Any questions on that? So the key here is you have to be aware of the information that's given to you, and you need to decide if it's an echo or actually just to get to the object. You'll have to kind of think it through and decide, do you have to double something? Do you have to have something? And really, there's often more ways to go about it. But at the end, no matter how you went about it, that would have been your answer. So you could have figured out how far it is. If we went ahead and used 5 seconds, we could have went ahead and figured out how far at 343 meters per second, how far it is to the wall and back. But then at some point in time, we would have had to half that to figure out the distance just to the wall. But at the end, we got that answer right here. Okay, so the next bit right here. Do you have this picture in front of you? Did I give you the picture? Okay, what I want you to do is I want you to write down audible and go ahead and put 20 to 20,000. Actually, let me draw it up here. Audible. That's going to be 20 to 20,000 hertz. Just draw right here. And then below that is going to be infrasonic. It's going to be 0 to 20. Maybe we'll put 20 hertz right there. 20,000 hertz right here. So audible is going to be in between those. And then below that is going to be called infrasonic. And above that is going to be called ultrasonic. So audible sound, yeah. Just anywhere on the side. If I ask you what sound, what's the frequency of sound that people can hear, you should be able to tell me 20 to 20,000 hertz. And if I ask you what's that called below it, you should be able to say infrasonic. So yeah, some animals that can, like elephants can communicate, maybe because of large ears or something. They can communicate and they can sense things that we can't sense. And then we would call that hearing for them because they can hear infrasonic. Excuse me. And then above that 20,000 hertz is going to be ultrasonic. I know it's in your notes, but it's a good idea to have it somewhere because you're likely to have this question asked, straight up question. You remember 20 to 20,000 is called hertz, or it's called audible. You get that question right. We good there? Let's go ahead and let's test our hearing out. Now I'll tell you right now, just a little caveat. This is only as good as your speakers are. So some of you at home might be able to hear differently than us in class. And there's also two things that go into hearing. First of all, volume, and let me just go ahead and play a noise. Everybody hear that? Well, there's volume, and that is associated with amplitude, and we'll see that later on. But amplitude, you first of all have to be able to, the frequency has to be within the frequency that you can hear, and what you perceive is called pitch. So the frequency has to be between 20 and 20,000 for you to be able to hear it in the first place, but it also has to have enough volume or enough amplitude. It needs to have enough density of that wave for you to be able to sense it in the first place. So let's go ahead, I'll move it down. I can still seem to hear it under the 20. It doesn't do a really great job. Can you hear anything there? Yeah, you should be able to hear until it's 20 hertz. But let's just go ahead and I'll turn this up a little bit. Hear that? So that's 130 hertz right now frequency. So we're in the audible sound below the 20. So if I go all the way down here, we're in infrasonic. You're not supposed to be able to hear it. But if I go from 20, I start getting a little higher. That's over 4,000 right there. 4,000 hertz of frequency. And what are we supposed to be able to hear up to? 20,000. So right now you can hear it because it's in the right frequency. It gets a little annoying. And I used to have better hearing 2 years ago. I think last year, I don't know if I did this because we were already on that lockdown or the COVID thing at home. But right now, it kind of seems like it disappeared. Let me be quiet. Let me turn this up a little bit. Can you hear that? I can kind of sense it. You still hear it? You hear it back there? Yeah. My mind, I'm going. I guess past 2 years, I just went from being young to old. Can't hear it anymore. And so we're just at 16,890. You hear it? See if I can turn up. See, like last class, some people could hear it, some people couldn't. So when I did this, Well, if you couldn't hear it, it wasn't really annoying to you, but the people that actually could hear it, it was getting really, really annoying because I just went ahead and turned up the volume of whatever they were hearing. And so this right now, once you get to 20,000 and we pass up that 20,000, so this is right there below 20,000, then we get into ultrasonic. And there's a lot of uses for ultrasound. We hear it. I kind of, sometimes it's just like a sense. I don't know if I'd call it hearing, but I almost can sense it there. It's just like an annoying, really, just annoyance. But I have a link if you want to test your parents out, check their hearing. See, I can definitely hear. That's pretty annoying to me right now. About 12,000 hertz. But anywhere between the 20 and the 20,000 is audible sound. Below that, you're not really supposed to be able to hear. Once again, it also has to do with the speakers and other things. Not just some of this frequency might not be exactly 11,720. So I'll close that off so we don't have to hear it anymore. Somehow it's still kind of stuck in my head after I'm done, after I close it off. And let's go ahead and finish off the notes so that you can do a little practice and we can start getting ready for our midterm. Okay, so look up here for a second, because when I say the loudness, and go ahead and highlight this, loudness is the amplitude of sound. So, well, how is it amplitude if a sound wave is a longitudinal wave? Because I don't see an amplitude in this bottom part. Well, if you went ahead and you graphed the density, you would have amplitude. So really, in a way, we call it amplitude, even though this is not a sound wave, but this is a graphical representation of the density of that sound wave. So if I was taking a look at this and I said this was A and this was B, which of those two waves would be louder? A or B? Which one would be louder? Based on density, which could be graphed as this. Which one would be louder? Which one has more density? A or B? A. Which one has which one would be perceived as having a higher frequency or higher pitch? Yeah, it would also be A. So A, if you take a look, the wavelength is the smallest. Take a look at this, wavelength is bigger. So if the wavelength is smaller, that means the frequency, you can get a whole lot more frequency, a higher frequency, and therefore you would have a higher pitch. And I'm still hearing that sound in the back of my head right now. So just a reminder, since sound is a mechanical wave, it's not going to travel in a vacuum. It's going to get faster in a gas, faster in a liquid, and even faster in a solid. The more density, the faster it's going to travel. Also, temperature is going to matter. And when it comes down to temperature versus elasticity, a solid's always going to be faster than a gas. But within let's say a temperature, let's say a 5-degree temperature, 5-degree gas and a 10-degree gas, it's always going to be faster the higher the temperature. But once you go into the next phase of matter, you're going to have liquid always trump gas, solid will always trump liquid for speed. And so this is just showing you, like, if you have sound traveling through iron, so a lot of times they'll say, you can try to listen to the railroad tracks. If you listen to railroad tracks, you can hear the train coming a lot further or a lot sooner. It's not very. There's other reasons behind that, but sound would travel that locomotive coming down the railroad track. You're going to hear it a lot quicker because of the speed that it's going to be traveling. So here's our equation. We're going to finish off with a couple more questions. Give me your attention up here, and then you're going to finish off the class on your own after we're done with this. So here's your equation that I've told you before. If you know the temperature in Celsius, you're just going to multiply it by 0.6, and you're going to add 331 to it, and you're going to have the velocity of sound. This one right here, you don't have these questions in front of you. I just want you to, on the side of your page, just write down A, B, C, D, E, F. Let's go ahead and do a quick review of what we covered up till now, and then we'll finish off with a little math. Just write down A, B, C, D, E, F on the side of your page. Don't write out the question. Just go ahead and put down your answer. Try to beat me to the punchline before I say the answer. So what kind of wave is sound? Give me the two things. Is it electromagnetic or mechanical? It's mechanical, and then is it longitudinal or transverse? There you go, perfect. So it's mechanical, longitudinal. I know in previous years that was a question on most tests. It probably would be one again. What range of frequency can humans hear? Between 20 and what? 20,000. What do we call this? The sound we can hear is called audible sound. Good job. Above it's called ultrasonic. Below it's called perfect. And what property is related to the loudness of sound? That's going to be the amplitude. Good job. So you're ready for those basic questions if you can answer those. And then let's go ahead and answer a few more. This is where you have 5 degrees Celsius ice or 23 degrees Celsius water. So normally, if I was just looking at temperature, 23 would be faster than 5. But I have to look at this first. Yeah. Solid is always going to be faster than a liquid. So you might want to write this down. This is what I was talking about before. Temperature is important. Higher temperature, the faster sound goes, but it will always be faster in a solid than a liquid. So if it's changed its phase and it's already in a different phase, it might not work itself out. You always want to look. If this was 5 degrees Celsius water and 23 degrees Celsius water, it would have been the 23 degrees Celsius water. But this is not. This is ice and water. And unless you did something special, most likely you're not going to have, negative 5 degrees Celsius water. It would be ice already. Got it? Okay, go ahead and do this one. Do that. V sound equals 331 plus 0.6 times temperature Celsius. Write that up and go ahead. You have your temperature Celsius right there. Go ahead and tell me what the velocity of sound is going to be when the temperature is 10 degrees Celsius. You get it? What's your temperature going to be? You should have got 337 meters per second. Is that what you got? Then one last question together, but then I want you to keep on working on your own. How long would it take someone at the top of the Eiffel Tower? So I'm going to draw my poor version of the Eiffel Tower. So someone's up here at the top of the Eiffel Tower, and someone's down here. How long would it take them to hear yelling 300 meters away? This is not an echo problem. On a day the temperature was 15 degrees Celsius. So do the V sound equals 331 plus the 0.6 times temperature Celsius. And then after you do that, then go ahead and do the V equals X over T, solving for saying how long. So solving for T, rearrange that, it's going to be X over V. Go ahead, do this, and then plug that in over here, and go ahead and get your answer. So if the 340 meters per second sound had to travel 300 meters, so that's me plugging in the numbers, your final answer would have been 0.882 seconds. Is that what you got? Once again, we were given the temperature, and we had to realize, and this is where you have to realize this, you had to realize the question, all you have to be given is temperature. You might want to write that fact down inside your paper. If you're given temperature, from here on out, for sound, you can calculate the velocity of sound. So if I give you the temperature is 25 degrees, and I gave you a time, and I ask you how far does it travel, you're going to have to do a two-step problem. You're going to have to come to this velocity of sound, and then you're going to kind of work from there. Any questions here? Okay, so this is what I want you to do for the rest of the period. If you're at home, you're going to be working this for the rest of the period. This will take you to my Stickman Physics website. I want you to keep on working the problems, and then as you go, and if you link through this, you're going to see the little, the questions that you have on your notes in front of you, and you'll have you have the little thing that says show answer. And if you click show answer, it will show you the answer. So I want you to work on these problems, get some more practice right now for the rest of the period. And then make sure that you click show answer so that you can just check your work.